Okay, great. So we've got one more talk in this session, and that is by Chaitan Baru, who's, like Mike, a recovering database person, and myself, who's been spending the last couple years at National Science Foundation spearheading a bunch of the big data efforts that are coming out of SCIES, which is the computer science part of National Science Foundation. So he's going to give us an update on what he's been doing and how some of his friends at NSF are thinking about big data and data analytics. And let me try to help you out with this. Yep.
All right. Thanks very much, Mike. It's certainly a pleasure and an honor to be here at the end of project meeting for AmpLab. So first, congratulations for clearly what seems to be a really fantastic success. As you heard repeatedly, and as we at NSF like to repeatedly remind people, NSF has invested in this project. It's one of the expeditions project which I think, as Mike mentioned, is an extremely sort of difficult competition to come through. It's a large amount of money as far as NSF is concerned, $10 million. And we couldn't be more thrilled by the success of this project. I have to say that my boss at NSF, Jim Kurosa, who's the assistant director for SCIES, would have really liked to be here to speak. He was unable to come due to other engagements, and I was happy to come because I happen to be from San Diego first, and my daughter is here in the ECS department, so I'm happy to be here. By the way, from what she tells me, by their reckoning, this is the undergrad kids, 89% of EECS is male. So you might actually find her because she's only the 11%. So what are some of the things I wanted to say? I think there's fantastic talks this morning that really set up the background for some of what I'm going to say. I think it's actually a fantastic idea to actually have an end of the project meeting. I can't remember if you said this is the tradition at Berkeley or you started the tradition, but I wish this is certainly one of the things I'm going to carry back is it'd be great, especially for these large projects. And actually, I myself have been PI on some of those kinds of things where we have not had an end of project meeting. But I think that's really a good idea. It's a good way to step back and look at it. Now, of course, it's a great idea when the project is so successful. But by and large, I think that's a good thing to do. The other thing that really impressed me is kind of how the project started, right? I mean, you talked about how both of you, Jan, yourself, maybe some of the other folks involved in the project were in industry, learning something, seeing some things, and then that kind of came back. So this idea of interaction between academia, industry, and I hope government, especially when it comes to big data, I think is a fantastic idea. And in fact, I mean, we really like AmpLab. As you saw the timeline, when it got funded, soon after that, or around the same time as when the Obama administration announced the Big Data Research Initiative. So AmpLab actually was one of the projects that was featured in that first meeting that talked about it. And ever since then, we do point to it as one of our poster child projects. And not least because Tom Khalil is at the White House, and I think he has some familiarity with this campus. But what I wanted to say is what AmpLab has created, and it may be part of the Berkeley ecosystem as well, is this nexus between industry and academia, which is also something we have exploited in another new initiative we've just started at NSF called the Big Data Regional Innovation Hubs. And I think Meredith Lee is here somewhere. She's the executive director for the West Hub. And that's, for us, is another very exciting initiative for community building. And hopefully, it's kind of a area that might give rise to things like RISE Labs or other ideas of that nature. Okay, so that's, I think that's all I wanted to say by way of introduction. The only last thing I wanted to mention to react to one of Mike's comments is, so I'm a rotator at NSF. As I said, I'm from UC San Diego. And I was recently asking one of my Fed colleagues who's a permanent Fed about this idea of can we take money back, right? So if you funded a project can you actually take money back? And the answer is no, we can't. And that has nothing to do with AmpLab, but I can tell you I've seen certain projects where my thought is, gee, how can we take this money back and do something better with it? Anyway. Okay, so let me launch a little bit into sort of, I suppose, some of the current thinking and what we are looking forward to. And you heard about the next 5, 10, 15-year kind of discussion earlier already. The Expeditions project is funded by the SAIS Directorate. All the divisions in SAIS are involved. That's the org structure. You don't need to be able to read it. There are 4 divisions in computer science, and each of them has division directors. And there are a couple of senior advisors, so I'm one of them, and Peter Asperger, my colleague, is the other. And so we work with Jim Kurosa, who's in the so-called, what we call the so-called front office. Okay. The context for some of this is NSF recently went through this exercise of identifying sort of big ideas. And this is, again, in a way resonates with the previous talk about about the hard problems, the things that, clearly that basic research would do, like industry may not do, and so on. I won't go into the details of some of these early slides because I really want to make sure we have enough time before we all get hungry for lunch to talk about some of my latter slides and also maybe have some time for question and answers. But there was an exercise at NSF to try and bubble up ideas for what these big research, visionary research ideas should be. And that graphic shows you the set of 6 research ideas that are on top, and then there are 4 what we call process ideas at the bottom. In the middle, as you can see, is data science. Now, as a data guy, I wish there was only one big idea, which was data, and that everything else was connected to that. Well, unfortunately, there isn't, but all of the other ideas that we are looking at, data clearly plays a very important role. So in fact, as we go forward, we would be trying to make sure that whatever the data agenda is also links to the others. So quickly, some of the other ideas there are, one is about navigating the new Arctic. Maybe it's the flip side of thinking about climate change, but there are lots of things going on in the Arctic, and there's a lot of research interest in observing those things. The other is work at the human-technology interface. So this is sort of generalizing the notion of just human-computer interface, but the fact, and again, it was mentioned, the fact that there is so much, we're surrounded by so much technology, including data, what is that doing to the human-technology interface? The third is basically genomes to phenomes, understanding the origins of the code of life, basically, and that's really driven by biology. And the next one is quantum leap, the next generation of technologies in quantum technologies. And the last one is what's called windows on the universe. These are all sorts of new ways that we now have, including gravitational wave observatories, new kinds of telescopes, et cetera, for observing more deeply phenomena going on in the universe. And as you can imagine, all of these have connections to data in very interesting different ways. For the universe, it really is the big data question, right? Lots of data probably coming at you at very high stream rates that you have to make some decisions when you get data tonight about what you need to do the next night, and so on and so forth. The genomes to phenomes is very heterogeneous data. There could be little data, big data, but it's a combination of very heterogeneous things. So it's an exciting time. I won't go too much on the process ideas, except to say that one of, well, actually, there's a couple, well, maybe quickly on a few of them. One process idea is this notion of convergence. And convergence is really talking about that all of these complex problems that we are now looking at really need a holistic approach. That is the multidisciplinary approach. And I think that what that means from a process point of view is increasingly you will see solicitations coming out of NSF that will involve more and more multiple directorates coming together. And so again, I think what you did in terms of starting off AmpLab, and at least some of what I've heard going on in this campus through folks like Dave Culler and so on, is that, and I think your Vice Chancellor hinted to something like this happening on this campus. I think those kind of cross-college interdisciplinary things will be very important. The second one there is about inclusion, and that's, again, an important thing. This is underrepresented minorities and getting more of them engaged. We're particularly concerned about that in data science, because a couple of years ago, if you notice there were a lot of articles about how data science could be this new field that would be better for underrepresented minorities, including women and so on, because it had the connection to data, which means it had the connection to real applications and real things going on. And there's a segment of population that resonates to that. Well, the reality is, so far, we have not seen that, right? So that's a concern. The third process idea that's important to us is this notion of mid-scale infrastructure. So very quickly, if you look at NSF programs right now, the regular solicitations will go up to, say, $20 million or so. These are the big centers and so on. And then there are these other projects that we call major research construction facilities. They start at about 200 million, 300 million, and so on. And those are the new telescopes or the new detectors, et cetera. So there's this gap between 20 million to 200 million that there is no real vehicle for funding efforts at that scale. So that's the new process idea about how we would set processes internally to allow those kind of funding. And that's important because we think some of these big ideas, including the one on data, might fall in that range of $70 to $100 million initiatives. Okay. That's a little bit washed out diagram. I won't go too much into that other than to say, this is actually a data representation, so you could spend an hour just talking about this diagram, about how the data was derived for it. But one of our analysts at NSF took the statements sort of that were written internally for these 6 big ideas and looked at the current set of proposals that are already within NSF. So these are not new things, past efforts, and tried to classify projects based on sort of the text that was there. So it was a text analysis kind of experiment. And then what they tried to do is to see how many of these proposals involved multiple directorates. So what that diagram is showing you is kind of linkages between proposals that nominally fall into these big ideas and showing how there are multi-directorate connections. And you may not be able to see that very clearly, but it shows that the harnessing the data, which is on this. So on the left-hand side are all the ideas. On the right-hand side are all the directorates. And the harnessing the data idea actually connects to all directorates. I think the only thing I'll mention there is, so internally what's happening right now at NSF is there are working groups being formed to start looking at strategies for how to go forward in each of these ideas, next 3, 5, 10-year plans. And clearly for the harnessing data working group, all directorates would be involved. In fact, there is a lot of enthusiasm from all directorates to be involved. And I think there is recognition that SAIS, computer science, would lead it, but we would do this in a very collaborative way. So in some ways, I hope that also reflects the kind of collaborations going on campuses. So what are the themes of the harnessing the big data? So there are research themes, there's education, and then there is cyber infrastructure. So the research themes kind of fall into these 3 categories of foundational work, so building up the theories related to data science, basic theoretical and principles of data science. There is systems foundations, and maybe a lot of what AmpLab did would fall into that kind of thing, building the systems, understanding what it means. And just before in the break, we were having an interesting conversation about how might you engineer real-time systems, to be able to do things like dealing with errors and debugging and all of that. And my own suspicion is if you don't think about failure modes and debugging modes, et cetera, right at the start of architecting these systems, they have no hope of dealing with those things once they're in production, right? So those kind of foundational things. And then the third circle there is data-intensive research. That is, research in all of the domains of science and engineering that are being driven by the fact that there's a lot more data of all sorts, right? Whether it's big or variety and so on. So those are the research themes. We're also very interested, obviously, in the education and training aspects, not just in the short term. Clearly, we all recognize that there is a shortage right now, whether you're talking in data science per se, or the use of data in all of these sciences. Everybody is hurting for skills and experience and training in those areas. But also, we are interested in looking at 5, 10, 15 years ahead, what would this field look like? And finally, cyber infrastructure. So if data science is one of these things where just as computers were very important in the good old days, some of us here are now old enough to remember times when, getting a workstation on your desk was a big, big deal. And universities were known for the fact that they could actually get grad students their own personal workstations. Well, we are now in that state with data. Getting access to real data is a big deal. And as you heard, companies like Google, et cetera, leap forward because they actually have the data. What about that issue in academia, right? So we are looking at what is the infrastructure needed to push data science research, everything from the hardware to the data, the networking, and all of that. So investments in harnessing data would be across all of these areas. Now, let me give you a quick diagram to show also how we are thinking of how you might sort of notionally architect this whole thing when you think about this as NSF-wide and across all sciences. So you have the standard layers of, there's a basic infrastructure. There are some services, very broadly speaking, some software capabilities that sit on top of this infrastructure. And then there are what you might think of as, what we might in computer science and data science think of as applications, and these are really the science folks doing their things. And gateways to these environments might be one of those things that you would have. At the infrastructure level, clearly this is storage and compute. So the analogy you can draw to this is back in the mid-'80s, NSF invested in supercomputer centers, and the infrastructure was supercomputing. By the way, when they did that, they also said, no, let's think about having some high-speed network connections between these supercomputer centers. That was the NSF net, which was the progenitor to the internet. So what we are saying today is, just as you had that kind of infrastructure in those days that really pushed forward computational science, but, oh, by the way, created internet on the side, today, when we deploy these kinds of infrastructures, it should be storage and compute, right? So that seems obvious, but it'll make that point, which implies, by the way, networking under there. NSF has already invested a lot, and that thing at the bottom is networking. So NSF has already invested a lot through various programs called CCNIE and CC Star. Some of you might know this. For campus-level networking, so 100 gigabit connections on campus, high-speed connections across campuses. We think the infrastructure game is going to have participation at the campus level, so campuses are doing different things. Regional level, so maybe the UC system might be doing something, or the, say, North Carolina University system might be doing something, et cetera. So they would be players in this. Commercial folks will have a role. So we have cloud providers. What kind of role would they play in future? And the national contribution is where NSF comes in, and there could be international connections as well. When you talk about services, for all of this to work, there is some core set of services you need, of course, whether it's distributed file system management, authentication, et cetera. And by the way, those the interesting thing is sort of similar to the supercomputing analogy is those have to be robust and production quality. That is, this is not, if this is infrastructure that scientists must be able to use for doing their data-oriented research, then some of this stuff has to be pretty robust, okay? But then it also opens up opportunities for us to try new services on top of that, which is what this green circle is. And the services could be broadly in the areas of discovery of data, access to data, analytics, semantics, et cetera. So I won't belabor this too much, but as you go from top to bottom, you're talking about sort of more shared services and more shared infrastructure. So, it doesn't matter whether you're doing biology or physics. At some point, you need high-speed, efficient access to storage, for example. And as you go from bottom to top, you're talking about more specialized applications. So at the applications level, the kind of codes that the biology folks might be running might be different from what the astronomy folks are running, and so on. And then there's a whole issue of that NSF has to worry about is, the governance and sustenance and management of all of these. What we would like to do, this is the desire, and this might, again, resonate with some of the things going on in campuses in terms of trying to share and do things across divisions, is to have an infrastructure in place that could be used by across the board by all directorates and all different kinds of sciences. So the bubbles on the top are understanding the brain and the National Brain Observatory. So that's a neuroscience initiative. The next one says Infuse is the nexus of food, energy, and water systems. That's another initiative that NSF has. Involves geosciences, engineering, a little bit of biology, and certainly a lot of computer science. The third one is called Smart and Connected Communities. That's the whole smart cities area, and clearly real-time, et cetera, would be important there. And the last one is basically the major research facilities that I mentioned. Okay, so let's see, all right. The guiding principles for all of this, and as you heard today, some of the recipes for success is it should be open data. Data should be free, openly accessible. Doesn't mean that it's all free. There may still be some access controls. There may still be some protocols of how you share. But in general, it should be openly accessible. It should be open system so that you could extend it, add new capabilities, and so on, and open source, right? But then there are going to be data resources in here that will require some levels of access control and privacy and so on. Looking to the future, now let's talk about some of the ideas we are working on, I guess right now, looking forward to the future. I think what we are seeing, especially in this area of data science, is this sort of three things happening. There's clearly the data-intensive fields, right? Which is really was the original tail that sort of wagged the dog. I mean, you just saw a lot of data, and people said, "Gee, what do we do with all this data?" So, whether you're talking about genomics or engineering, smart manufacturing, physics, high-energy physics, astronomy, and so on, they're all being pushed by a lot of data. So there is the data-intensive science aspect, okay? What is emerging clearly now is foundational aspects of data science. Now, what are the principles and foundations? And in the middle, what we like to think about now is this idea of translational. So how do you do, so the translational data science idea is the application of all these foundations and principles to real-world applications. So if you think about it that way, it also is a good way to think about how programs could roll out at NSF. And actually, current programs kind of map into some of these things already. But it's sort of a good taxonomy to think about research activities: foundational, translational, and then data-intensive research. I won't go into this diagram too much. It's really just making that case. The other case I wanted to make here is when we say data science, it really is data science and engineering. And I think you heard that engineering term being used in one of the previous talks, that there's a lot of this falls under the engineering category. And translational is really the application of one to the other. And there are many fields that benefit from this, and your traditional science and engineering fields, but I put additional things there, may not be able to read at the back, which are things like health, finance, agriculture, metro systems, meaning smart communities, criminal justice, policy, et cetera. These are all, you may not think of these as traditional sort of NSF areas, but NSF is also engaged with a lot of other federal agencies, and some of these are big, big issues that are out there in society. And that's another way to think about what we could be doing is, as academia and NSF, is facilitating use of data in certain areas that may not either seem highly profitable or may not seem as sexy to begin with. Just as a quick aside, now I live in Washington, D.C. I happened to go to a talk 2 days ago by Senator Cory Booker, who's from New Jersey, and he was talking about the criminal justice issues, and some of you here may be working with that community, but the criminal justice issues in this country are actually horrendous, and they're happening every day. And as I'm standing here talking to you, it's actually going on. So data could actually make a difference in those kind of things as well. Okay, a few more slides, and then I'll be done. So I did mention that those three circles of foundational systems and data-intensive research. So we've already started doing something in the foundational and principles area. So there is this call out, solicitation out from NSF. Some of you may be familiar, called tripods, which is transdisciplinary research in the principles of data science. The transdisciplinary there refers to the notion that we want these projects to deeply involve computer science, statistics, and math all together, and not each working separately, just coming together for a project purpose, but really developing new theories and new ways of looking at things for the entire data life cycle, not just the analytics part, not just the sort of fun, sexy part of doing analysis with the data, but everything from collection, cleaning, error representation, error management, use of error then in the analytics, and all the way down to retention and long-term preservation, et cetera. I mean, if you pick one notion of, say, data value, there are huge, interesting questions about, how do you assign value to a data? And how do you assign value to this, the next piece of data you want to collect, or the next piece of data you want to analyze, or the next data that you want to delete from your system? So it's meant to cover the entire life cycle of data, not just the analysis part, and it's required to bring all these three disciplines together. I'm not going to read through all of the stuff here, but all of the stuff here just makes the point that we are very much interested in the full set of issues, including things like reproducibility and so on. So that's where the solicitation is. If you want, I can leave the slides behind, but anyway, you can do Google search and find all the information. We just had a webinar on this a couple of days ago, so there is a whole webinar online as well. Talking about other things, so that's already in place, but we really need to think seriously about infrastructure and systems. So what kind of national scale infrastructure and systems could we deploy? When I say we, you know that NSF itself doesn't do anything, right? 94% of the money that comes to NSF goes to academia. So it has to be through the community. So it has to be through universities and so on. But what should that infrastructure look like so that there is some commonality? We're actually increasingly becoming tired of sort of funding one-off hardware, for example. Last year, we actually had some grants where people were asking $50,000 for a big cluster, and we said no. We're not going to fund these kind of individual hardware requirements anymore. You got to go find computing on other infrastructure we may already have funded, or maybe look in the cloud and so on. So we do want to create some common infrastructure, and how do you do this? So what are the needs? How do we go about finding out the needs? Ramanathan Guha, who used to be at Google, we work with him on certain initiatives, and he has this nice way of saying it. Today, we are not able to do the hello world problem for big data in academia, right? So the problem would be something like walk up to a petabyte data set, pick 10 terabytes out of it, and do something very simple. Just do a SQL query or something, and do that as a homework assignment. I give it to you today, give me the answer tomorrow. Can't do it. So how do we start with simple sort of challenges like that, and how do we make progress? So do we need community workshops? This is something we'd like to hear from you. Now, how would you structure this? They shouldn't just be computer scientists talking to each other. You have to bring in the users and the community, and you heard that today, too, the power of having the users involved. The infrastructure might involve hardware platforms, including networking, but might actually involve real data sets, software stacks, distributed test beds. Increasingly, we have big programs in cyber physical systems, which is now smart and connected communities. We get lots of proposals, people looking at streaming data and smart cities and so on. I was actually talking to Lynn Parker, who is my colleague. She's the division director for IIS, one of our divisions. And in future, there's all this IoT and robots and all of these mobile platforms. What should test beds look like for that, for academia to be able to do research? We've had some meetings where some of these things have come up, so I'm just trying to highlight some ideas. So when you have these large, complex data sets, it's not just SQL simple queries anymore. Non-procedural query language is a great thing, but I think you want to be able to do a lot more with your data. You want systems that do question answering, which already in commercial world, you're beginning to see some of that. Storytelling, dialogues. So you have the same data set, but you'd like to have multiple different interfaces. You also want to have interfaces, talking about the human technology interaction part. You want to have interfaces that may be cognizant of the expertise of the user. So if the undergrad is asking something versus the grad student or somebody who's an expert, the system should be able to give you appropriate kinds of responses. ML systems. So this actually, we had a meeting with some industry folks, and they mentioned this, that there is too much of a one-off going on right now when we build these machine learning systems. So how do we As Mike said, I'm a recovering database-aholic, I guess. I think one great thing that database systems have done, and Mohan is here, is build robust systems that work very well, okay? So by generalizing concepts like concurrency or whatever, ACID. So how do you build these kind of more systems level things that look at the whole life cycle of data, and not just one part of it? Another big area of interest, we have funded a lot of work in this, and you'll see more coming in future, I think, is reproducibility. And I think, as I said before, in terms of debuggability of real-time, I think reproducibility is one of these things that increasingly I'm convinced that it has to be built into the system. And also, even from a funding point of view, I think we have to build in reproducibility into the system. What I mean is, if we give somebody X amount of dollars, then some fraction of that X has to be to ensure that you're doing reproducible work, right? But it's a big, actually it's intellectually a very interesting challenge, but it's also a big challenge, because the more and more that we are using data to make decisions in real life that affects lots of people and lots of sensitive things, this thing of reproducibility is going to always be there. I hope it doesn't come and bite us, but I think it's always going to be there. The last thing I'm going to say is, so when we talk about this sort of plethora of data, this rich world of data that we have just in academia. So I have data from independent PI projects, independent researchers doing their data management plans and doing whatever it is with their data. We have small groups that have come together and have funded data repositories that are useful for that group. You might have institutions like the California Digital Library or other places like that that deploy infrastructure also for data. And there are also large facilities like NCAR, the National Atmospheric Research folks, who have petabytes of such data. So with this, we have this very rich, wide variety of data across all disciplines. Going back to that diagram I showed you, that if we as the CS data science community are trying to do something that all scientists could benefit from, then we are talking about some very heterogeneous collection of data. And what would be nice is that if we could conceive of a set of simple services that could provide people access to this. So you might have heard, some communities have started talking about FAIR, findable, accessible, interoperable, and reusable, right? So I have some simple ideas of what are the kind of services robust services you could provide, but it could also be, in addition to being robust, is also an environment where you could be doing research that allows you to get to this vast richness of data that maybe standard commercial folks are not necessarily looking at. Some of this may go back into being commercial, and I think it will. Some of the science stuff actually is of great commercial interest. But it's also a good platform for research in our community. So along these lines, one of the things we are looking at is this notion of creating sort of an open knowledge network. So again, this comes from the idea that some of the big companies, Apple, Google, Amazon, et cetera, and we actually had a meeting where several of those companies were in the room, along with academia and some agency folks, are building big knowledge networks, but for their own purpose, right? They're building it to sell you more stuff or to answer your query on Siri or whatever it is. But even they seem to be aware that some level of effort in academia would be a good thing even for them, if only because that means they get students who are actually trained on these large-scale environments. So actually, we have been working with Andrew Moore, who's at Carnegie Mellon, and Guha, and a few others on this. And just this morning, I had a call with Andrew. What we are thinking is maybe have an event in Silicon Valley to just discuss this. This is very much at a community discussion building phase. Okay, so maybe have a meeting here soon, but not soon enough in the sense it'll be next administration. We were trying to do this before January 20th, but I think it'll be after that. And then maybe follow it up with a meeting in DC, just to talk about what is the kind of thing we might be able to do. And what Andrew mentioned to me is he gave this pitch. He has 75 slides on this that he agreed to share with me, but he gave this pitch at CMU recently, and there was a lot of enthusiastic sort of support for this idea. That's one of the things we're looking at. So hopefully that gave you some sense of where we are trying to go. And that's all I have.